Okay, today we're going to talk about energy and chemical reactions. So we've just talked a little bit about balancing chemical equations and what a chemical reaction looks like, and we said that these chemical equations give us a visual interpretation of the chemistry that's actually occurring. So this reaction in particular says that when I react together two molecules of hydrogen gas with one molecule of oxygen gas, I can get two molecules of liquid water. So that's this chemical reaction. And if we're actually thinking about what happens here, if I was to draw these in their Lewis dot structures, then I'd have two hydrogens that are bonded together here, and I have two molecules that are doing that. And then I have one oxygen that's double bonded. We said that oxygen needs to share two pairs in order to have a full valence. And then that gives us two water molecules. So it looks like this. This is our bent water molecule, with our little Mickey Mouse ears for our lone pairs. There's a lone pair here, and two hydrogens. Okay, so if we're looking at the Lewis dot structures, then this is what's actually going on. And if we're kind of interpreting what's happening in this reaction, we can see that some of the chemical bonds are being broken and others are forming. So I have to break this chemical bond, I have to break this chemical bond, I have to break this chemical bond, because none of these things are bonded together on the other side of my equation here. Again, this is my reactant side, this is my product side. So to break apart the bonds between my hydrogens and my oxygens, and then I reformed bonds between my oxygen and hydrogen here. Okay, so on one side of my equation here, I'm breaking bonds, and then I'm forming bonds. And anytime I am rearranging chemical bonds, so breaking some and reforming others, this is called a chemical reaction or a chemical process. So that's chemistry in general, is the breaking and reforming of bonds to form these different molecules. Okay. Now the way that this relates to energy is that it takes energy to break apart chemical bonds. That makes sense. These things are happy when they're bonded together. It requires some amount of energy to break them apart. And when you put them back together, then they're in a lower energy form. They like to share. The reason that they're sharing these pairs of electrons is to get to a full valence. They're happier when they have a full valence. So we had to break them apart, which made them unhappy. And then when they reform, they're happy again. So there's energy that is released when chemical bonds form. Now, depending on the bonds and depending on the stability of these molecules, then the amount of energy that is required can be different. Okay, so the more stable, the stronger the bond, the more energy that is required. And same with here. If you have kind of an unstable molecule, you're not going to get as much energy released. It's not as favorable to be unstable. But if we have nice stable bonds, water, for instance, is really happy to form water. So you'd release a lot of energy because these molecules are happy, they're in a lower energy state. So this is just kind of an introduction to kind of energy in chemical reactions in general. And there's this kind of balance between the energy that is required for a reaction to occur and the energy that is released when these chemical bonds form. So there's this balance back and forth, and we have two types of reactions that we can classify based on this balance between energy required versus energy released. And the first is endothermic, an endothermic process. You can see that I'm serious about energy because I'm in my red pen today. So endothermic reactions are reactions that require more energy than they release. So it takes more energy to break apart these chemical bonds than you get from reforming them. And again, we're talking about things in this particular video in kind of an introductory sense, in kind of a general abstract concept kind of sense. You can actually put numbers to this thing and quantify them, and this would be called the enthalpy of reaction, or delta H if you're in higher levels of chemistry. But for those of us in the introductory level right now, we're really just looking at the concept that some chemical processes are going to require more energy than they release, and those are called endothermic reactions. An example of this is diatomic oxygen. So the oxygen gas that's in the air, that's in the atmosphere, is very stable. It has this nice double bond. It likes to exist that way. You can break it apart into two individual oxygen atoms, but it's not as stable. So I'm going from a more stable state to a less stable state. Okay, so that difference in stability means that one side of this energetically is going to be favorable. So it's more happy when it's a stronger, more stable bond. So that means that it's going to require more energy to break apart this more stable side than I get out when I have two oxygen atoms just hanging out. And so energy has to be added to the system in order to make this occur. And the type of energy is actually UV. So if you talk about our electromagnetic spectrum, kind of our waves of light, then in the UV range up in the atmosphere, UV light is enough to split apart, or specific types of UV light is enough to split apart oxygen atom or oxygen molecules. So this is an endothermic reaction. Now you can have chemistry and chemical reactions where you're forming more stable products than you initially start off with, and that's called an exothermic reaction. Exo meaning heat coming from, thermic is your heat, so thermal or thermic in general just refers to energy or heat. Okay, so an exothermic process, exothermic reaction, more energy is released when we form those products. Now an example of this would be like a combustion reaction. A combustion reaction is the burning of hydrocarbons in the presence of oxygen. This is what occurs in car engines, for instance. So let's just take the simplest of our hydrocarbons, which is methane. It's one of our greenhouse gases. And when I react methane with oxygen, then the products that always form are CO2 and water. And kind of depending on the temperature, the water can be in either the gaseous state, as I wrote it there, not that you can see my little G there, I have a G in parentheses, or it could be in the liquid form. That's why you see liquid water or steam coming out of a tailpipe when it's really cold outside, because you have water vapor that comes out when you burn hydrocarbons in your engine. So this equation is not balanced the way that I've written it. Looks like I have 4 hydrogens on this side, so I probably need a couple waters over here. Now I have 4 hydrogens, 2 oxygens here, 2 oxygens here, that's 4 total. So I probably need 2 of these guys. So now I have a balanced chemical equation. In a combustion reaction, I'm breaking apart the chemical bonds in methane, I'm breaking apart my oxygen, I'm reforming bonds with carbon dioxide and water, and these are incredibly stable compounds and really happy to be this way, and so a lot of energy is released, and we can kind of think of energy as a product here that is coming out. So whereas our endothermic reaction, we required some energy for it to occur from an external source, here we are releasing energy, and that energy can be used, this chemical energy can be used to power something mechanical like an engine, so we can move around pistons and that kind of thing. So this is a combustion process. Any hydrocarbon that reacts with oxygen giving you carbon dioxide and water, and it's incredibly exothermic. It releases a lot of energy, and we can use that energy to do work, mechanical work. Okay, so those are the 2 types of reactions, and this really comes down to a theory that we use to model chemistry that's called collision theory. And collision theory says that all chemistry occurs because of the collision between molecules. So I'm just going to summarize that as chemistry equals collisions. Okay, so chemistry and chemical reactions are due to the collision between molecules. And these collisions will give hopefully sufficient energy to break apart chemical bonds, and then they can reform in a lower energy configuration and release their energy, and that's kind of our chemical reaction. So these collisions between particles give us kinetic energy. Okay, so we said that because of kinetic molecular theory, particles particles are always in motion, right? We can describe the movement of particles as everything is always in motion. Matter is always in motion, and the kinetic energy from these moving particles is going to be transferred when you collide two things together. So one thing is going to collide into another, and it's going to transfer into the other. So this pen is moving, my hand is not. When I hit this, then my hand is going to move, taking some of the energy from here. So this is kinetic energy transferred from one object to another. Now, if we have multiple particles that are also in motion, then they have their own inherent energy from moving around, and so that all just kind of builds on itself. Now, if these molecules collide together with sufficient energy, then chemistry can occur, and that's kind of the heart of collision theory, is that the kinetic energy from moving particles can cause chemical reactions to happen. And there's a minimum amount of energy that's required. You can kind of think about it this way. There's this hill that we have to get over. And here's my reactants, and here's my products. And in order to get from reactants to products, I have to overcome this hill in some way, shape, or form. So I could have, let's just kind of say that my reactants are this ball here at the bottom of my hill. And if I put in a certain amount of energy, and that ball rolls up to here, so whatever energy I put in down here, it pushes up to about halfway up my hill, then my ball is not going to go up and over the hill, right? It's just going to roll back down. So no reaction is going to occur. I'm going to stay as reactants. Nothing happens. Now, if I put in more energy, so here's another ball, and I put in my energy here, and then my ball goes all the way to the top of the hill, then if I can get it up and over this hump, then it's going to go around to the other side down to my products. But if I can't get it up and over that hill, that energy hill, if you want to think about it this way, so the overall energy of reaction, the amount of energy that it needs in order to go from reactants to products is kind of this hill. And this energy is called activation energy, the minimum amount of energy that is required to go from reactants to products. Okay, so that's the bare minimum. The bare minimum energy required to go from reactants to products is the activation energy. And that activation energy comes from the kinetic energy of the moving particles. And that's what collision theory tells you. Sorry that this video is kind of rocking all over the place. I must not have very stable, speaking of stability, I must not have a very stable connection there. Okay, so in general, chemical reactions require energy to occur. Once these things collide together and that energy is sufficient to make this reaction happen, then we form products. And once we form products, because of the stability of the bonds that form, some energy is released. And we can have a balance between these energies. If it requires more energy than you get out of it, then we call it an endothermic process. And if you get more energy out than it required to put in, we call it an exothermic process. So that's kind of the summary of how energy relates to these chemical processes. And as always, if you have any questions, please don't hesitate to contact me.